And I will share with you my iPad. Come on, I trust you, iPad. You don't have to ask me this every time. There we are. All right, fantastic. Okay, so you'll recall that last time we started talking about equilibrium statistical mechanics. And so what we did last time was essentially step through some of the fundamentals as to how we're going to think about problems in equilibrium stat mech and how to calculate things in equilibrium stat mech. And the example we came up with was a weakly interacting gas, right? So again, we had a box of volume V into that box.
Question about the gas, if I may.
Yes, please.
Is this an ideal gas?
So we'll get to that today. And so what we talk about today is going to be an ideal gas, yes. And then we'll elaborate from there. Okay, so into this box we place N molecules of our gas. So we put N molecules. Okay, and so what we're interested in specifically at this point is what's referred to as the microcanonical ensemble. Canonical ensemble that characterizes this gas. Okay, and so what microcanonical tells you is that what we're doing is looking at fixed constant energy. Okay, so typically we give that its own special name to indicate that we're looking at just one specific value, so we call that E naught. Okay, and by ensemble, what we mean is all of the potential arrangements of this gas that will give you that fixed constant energy E naught. Okay, and so the idea is that we treat each of the atoms and molecules as like a Newtonian ball. That is, its energy. So the example we used last time was a harmonic oscillator. Okay, so a harmonic oscillator of mass m that you characterize its position by some coordinate q. And we said that what we're interested in are all the combinations of the momentum. So that's just the kinetic energy, and the position, which tells you what the potential energy is. So we're interested in all the possible values of P naught and Q naught that will give us this constant energy E. Okay, and so what we showed was that what this gives you when you plot the behavior of this thing in phase space, that is where my coordinates are the positions in the momenta, that what you have here is, you know, some constant that's equal to one variable squared plus another variable squared. So in other words, it looks like a circle, or more generally an ellipse. Okay, so all of the possible combinations of P and Q that will give you this constant energy E live on a circle in this phase space that has a constant radius that's equal to the square root of this energy value that we're interested in. And so in other words, what we're interested in doing is counting the number of possible states that correspond, that live on this circle, essentially. Okay, and now with the assumption that the probability of finding the system in one of these states is a function of the energy, that's essentially just a fundamental assumption that we're going to make, then because all of these states have the same energy, they should all be equally likely. Okay, so in other words, what we do is we count the total number of states that we have available to us in this phase space. Each one of those states is going to be equally likely, and hence by determining the number of states, we can essentially calculate how much of its time is the system going to are you going to be able to find it in a given state. Okay. All right, so what we showed was that what we're going to do is, again, if we zoom in on this circle, what we're going to do is say, you know, a state is some specific value of Q naught and P naught that will give us this constant energy. And we are going to define a state as any values of P naught and Q naught that live within an infinitesimal distance dq and dp away from one of our available states. Okay, and so what we wind up with is, so what we're interested in now is essentially the volume of this state space in phase space. And so in order to count the number of states we have, what we do is we essentially take this circle and divide it up into a bunch of little squares, and we count the number of squares simply by integrating. And again, to make this computation mean something, we can't just integrate along a line because the volume of a line is 0. And so in order to make this computation mean something, what we have to do is to take the value of energy that we're interested in and kick it up by some amount delta E, so that we're essentially looking at an annulus here. And what we're doing is counting the number of these little boxes inside this annulus. All right. Okay, and so now what we wound up with towards the end of last lecture was how to calculate this number of states. And so we defined this quantity called omega, which is a function of the energy that you're looking at. So this is what's referred to as the density of states. Okay, and we define the density of states such that if you take this quantity and you multiply by the thickness of our annulus, that should be equal to this, essentially just counting the volume and counting the number of, so it's a density times a distance, which gives you a number, right? And the number that we're counting is the number of states. And so what we do is we integrate over all possible values of P and Q that live within this annulus. Okay, all right, so that's essentially where we left off on Monday. Now, the last thing I told you was that now essentially what we have here is, again, the volume in this phase space, because each one of the states is equally probable, essentially the probability to find the system in one of these states depends upon just the amount of volume that corresponds to it, right? Because all the states are equally likely. The states you'll be more likely to find it in are those which occupy more volume. All right, and so essentially this thing that we're calculating here is proportional to a probability. Okay, so in other words, it's essentially our probability density function that we've been talking about the previous couple weeks. And so now what I said is that if you have some function, whatever it is, f, and you want to calculate the expected value of this function for this gas, the way that you would do this, I said, was like this. You just take your function and then integrate it over all the appropriate values of P and Q that correspond to the energies that you're interested in. Okay, so that's what we left off with on Monday. So now it occurs to me that this is not quite correct. Not quite. It's close, not quite. All right, and so the reason it's not quite correct is that this quantity is now proportional to the probability. Okay, so essentially what this integral does is it counts the number of states that correspond to, you know, the given value of this function that you're looking for. And so this is going to give you some number that's proportional to the probability. But it's not quite a probability, right? To make it a probability, it has to be normalized. Okay, and for it to be normalized, what you would need is that if you take this integral, so for normalization, you would need this integral, okay, which we said was, again, proportional to our probability density. We need this integral times some constant to come out to be equal to 1, all right? And so to ensure that that happens, what we have to do is to take this expectation value and essentially divide by the total number of possible states, right? So in other words, if we want to calculate the expectation value of some function, it's exactly what I told you previously. It's just that function times dp dq integrated over the necessary energy values. Oops. But then we need to normalize this, and the way that we'll do that is just divide by the total number of available states. Okay, and that is that, omega. Okay, so omega times delta E, that is the total number of states, right? So we take this integral, we divide by the total number of states. That then is going to give us a probability, essentially. Okay, does that make sense? All right, cool. So now what we're going to do today, so all of this we talked about within the context of a really simple example of a harmonic oscillator, right? So the harmonic oscillator, that's not a gas, right? So we were essentially just working out the mechanics of how to do this with a really, really basic, simple example. And so now what we want to do is to take this kind of machinery and this way of thinking about things and actually apply it to a gas. All right, so that's what we're going to start doing today. I don't know if we're going to get all the way through it or not, but we're at least going to start. All right, so the problem we're going to work on here is what's referred to as the microcanonical ideal, for you, sir, ideal gas. Okay, so again, what do all these words mean? The microcanonical tells you that you're looking at the gas at a fixed energy, E naught. The word ideal, that means that the atoms and molecules of the gas are non-interacting. Okay, so in other words, you got two molecules of this gas and they pass right next to one another. They're like ghosts, man. They don't even see each other at all. They just don't interact with each other whatsoever. So now, what does that matter? So what that matters is because they're non-interacting, that means that you essentially don't have to worry about potential energy, right? Because typically, if you have two objects that are, some distance away from one another and they're exerting influence on one another, then this interaction is going to manifest itself as some potential energy function that depends upon their positions. Okay? And so by assuming that they are non-interacting, you essentially just don't have to worry about this crap. It makes it a lot easier to do. Okay, and gas, same deal. So the gas also means, so gas, what the gas tells you is that it is dilute. That is, there relative to the volume of the container, there are not that many. The volume of space occupied by the atoms and molecules is a small fraction of the total volume of the container. That's what that's telling you. Okay, so does that make sense? Let me make sure I've told you everything I want to say. Okay, so again, here is what our system looks like. It is a container. It has volume V. Into the container, we are going to put in atoms and molecules of gas. So up to this point now, it's exactly the same thing we said we were going to talk about on Monday. And now we're going to get a little bit more specific. So now let's talk about potential energy. Okay, so now the walls of my container are made out of some super material such that once you go past the boundary of the box, the potential out here, so the potential outside of the box is infinite. In other words, they ain't getting out of the box, okay? They're stuck in the box forever. The potential energy inside the box, we are going to define to be 0. So there's no potential energy inside the box, okay? So there's no, essentially there's no spatial dependence of the potential energy inside the box. There's also no interactions. okay, between the atoms and molecules of the box. And so in other words, what happens is that what this assumption allows you to do, along with our assumption of non-interacting atoms and molecules, is that there is no potential energy to worry about. Okay, as long as they're in the box, their potential energy is 0. And they can't go outside of the box because the potential energy is infinite. Okay, so that's what that allows us to do. Okay, so now this is really nice and simple. And so now what we can do is to write down our Hamiltonian for this system. Okay, and so again, what we do is we just think about an individual molecule. Okay, and that individual molecule again is just a monatomic, so it's a monatomic ideal gas, so it's just a ball. So it's just a ball of mass m, speed v, with no potential energy. And hence, the energy, well, hell, let me get all fancy about this. The Hamiltonian of the system then is just equal to the kinetic energy of my balls. Okay, the kinetic energy of one ball is 1/2 mv squared, right? Piece of cake. And then we just have n balls, right? So the total energy in my system is I just take the kinetic energy of one ball, I put a little index on it to indicate that there are multiple balls, and then I sum over all balls. Okay, and so in other words, I'm summing alpha here goes from 1 to, well, there's a little bit of a, before I say that. The box is 3-dimensional, okay? So the box is 3-dimensional. That means these velocities here, we have to worry about 3 components, the x, y, and z components for each ball, okay? So in other words, when I perform this sum, I sum from 1 to 3n, right? So it's n because I have n molecules, and then it's 3 times n because I have to keep track of all of the 3-dimensional components of my balls. Okay, and so now that's what it is written in terms of the velocity. You would never write a Hamiltonian in terms of velocity. That's bad. Don't do that. Okay, velocities are resigned for Lagrangians and such. If you write down a Hamiltonian, you should be writing your Hamiltonian in terms of momentum. Okay, so in terms of momentum, this is equal to this. Okay, piece of cake. And so now again here, I'm making the assumption with this that all of the atoms and molecules are identical. That is, they all have the same mass. All right, so that's why I don't have to put an index on the m. Okay, and so now what I have here is a constant 1/2m times the sum over the square of all of my momentum components. 1 to 3n. Okay, and to save myself some writing, this sum over all these momentum components, I am going to call that, again, my big fancy P. Okay, so my big fancy P is this sum over my alpha squared. Okay, so my Hamiltonian is big fancy P, whoops, I'm going to call that big fancy P squared, excuse me, big fancy P squared over 2n. Piece of cake. So there it is. That's my Hamiltonian. All right, so now what we're going to say is we're interested in all of the values of big fancy P that will give me some fixed constant value of energy, E naught. All right, and so now the question, so now that we have our Hamiltonian, the question we want to ask ourselves is how many states live between E naught and E naught plus some infinitesimal displacement. So it's just exactly what we talked about on Monday. We want to look at what the phase space of this thing looks like, We're going to kick the energy out by a little bit so that we can calculate a volume, and then we're going to let that delta E go back to 0 so that we're talking primarily about the things that live close to the surface. All right, so let's do it. Okay, so first of all, it's much easier to, so again, all the particles here are non-interacting. And what that means is we can just think about what happens to one particle and then essentially multiply that by 3n, right? So we just figure out how one particle behaves and then we do that 3n times. Okay, so first of all, let's just think about one particle. Whoa, what the heck is that? Let's think about one particle. Okay, so in other words, what does this thing look like if n equals 1? Okay, if n equals 1, then our Hamiltonian is just this, px squared plus py squared plus pz squared over 2n. That's it. Okay? And so now what does this phase space look like? So here, this doesn't even depend upon position, right? We don't even have Q's in here. The only thing we got in here are 3 momentum components. And so the coordinate axes of our phase space in this case are just going to be our momentum coordinates. All right, so my phase space is going to look like this. So this axis is my px, this is my py, and this is my pz. Okay, so it's just a 3-dimensional phase space where the coordinates are my momentum components. All right, so now what is this? So this again is just equal to some constant energy. And so what we have is just a sum of squares of our coordinates equal to some constant. So again, it's like a circle, right? Except it's a 3-dimensional circle. It's a sphere, a sphere. Okay, so our phase space in this, how am I going to do this? Let me do the surface with black. So our phase space surface here, what we're interested in is a sphere. Wow, that's a terrible looking sphere. Let me try again. Marginally better. And to indicate that it's a sphere, we gotta move into the 3rd dimension, man. Wow, it's like you're there, right? Okay, so that surface, so the surface of this sphere is, so all the states that live on the surface of that sphere correspond to the states that will give us this specific fixed value of E naught that we're interested in, okay? So our sphere here has some radius, which I will call big R. And that radius, again, is just simple geometry. So the radius of this sphere is just equal to 2m E naught square root, right? Because all I'm doing is I'm going back up here to my Hamiltonian. I'm moving all the constants onto one side. So I just multiply both sides by 2m and I get that. So now this is just equal to, whoops, the radius squared of my sphere. So that's just the definition of a sphere. Okay. And so now what we're going to have to start doing is calculating volumes in this 3-dimensional space. All right. So in other words, we're interested. So what we're going to do is we have our sphere with some fixed that corresponds to some fixed energy E naught. We're then going to kick that energy up by some small amount delta E. And so what that's going to do is to essentially enlarge our sphere. All right. So we're going to kick ourselves up to some marginally larger sphere. And we're going to be interested in this volume, the volume in the spherical shell. Okay, so in other words, what I'm going to do is I'm going to calculate the, well, shit, pardon my language, the volume of a sphere with energy E naught plus delta E. Okay, so that'll give me the volume of this blue sphere. And then I'm going to subtract the volume of a sphere with energy E naught. Okay, so that's the black sphere. And so when I take this difference, that'll just give me the volume of this blue shell. Okay, so in other words, what we're interested in is the volume of a sphere in three-dimensional space. So the volume of a sphere in 3D, you guys all know what it is, 4/3 pi r cubed, right? That's the volume. Piece of cake. All right, so that's how things work for a single particle. So now the complication is that we have n particles, right? And so now our Hamiltonian, if we go back here and we look at our Hamiltonian, I should rewrite, whoops. Let me rewrite this correctly to give the appropriate Hamiltonian. Okay, so now if I start adding particles on, I'm going to have a term like this for the first particle. I'm going to do exactly the same thing for the second particle. Whoops. dy2 dz2 over 2m. And I just keep doing that for all my particles to give me the total energy of this thing. Okay, so in other words, what we're looking at is not a sphere in 3 dimensions. We are looking at a sphere in 3n dimensions. That is a big ass sphere, all right? And so now instead of the volume of a sphere in 3-dimensional space, we are interested in the volume of a sphere in 3n dimensional space. Okay. So let me make sure I use the same notation everywhere. All right, so the volume of a sphere in d dimensions. So what is it? All right, so I'm not going to prove what this is to you. It's relatively straightforward. You just have to figure out, you know, what is the infinitesimal element in 3n dimensions and then do that many integrals to see what it gives you. So I'm just going to tell you what the answer is, okay? So the answer is that I'm going to call this volume mu for reasons I don't know, just because it's a cute name. I'm going to indicate the number of dimensions by putting a little d subscript, and my sphere is going to have radius r. All right, so it turns out that the general volume of a sphere in d dimensions is equal to this. It is pi to the d over 2 times the radius to the power of d divided by, and here's where things get a little weird, d over 2 factorial. Okay. All right, so let me prove it to you. So for example, if we try this formula, what the heck? Okay, I don't know what that is. Ah, and it's gone. So if we try this formula for d equals 3, here is what we get. All right, we get mu 3 with a given radius is equal to pi to the 3/2 times r cubed divided by 3/2 factorial. What the? How do you take the factorial of a non-integer? All right, so it turns out you can calculate the factorial of non-integers using something referred to as the gamma function. So using the gamma function, and so there's a problem in your textbook which you can work through in order to convince yourself that this is the case. So C problem 1.5 in your textbook. So using the gamma function, you can evaluate the factorials of non-integer numbers, And the factorial of 3/2 is equal to 3 square root of pi divided by 4. Okay, and so now when you take this and you plug it back into this formula, what you get is that the volume of a three-dimensional sphere of radius r is equal to pi to the 3/2 r cubed divided by 3 pi to the 1/2 divided by 4. Look at that, 4/3 pi r cubed, just like it should be. All right. All right, so this is the thing that we need to know. Well, not that, forgive me. This is the thing that we need to remember. Okay. All right, so now, what we want to calculate is, so let's calculate this quantity. That is the volume of our shell. So our shell volume per delta E. Okay. And so as I just elaborated, what this is the volume of our sphere we're in 3 n dimensions, where the radius is equal to E naught plus, is a function of E naught plus delta E, minus the volume of our sphere in 3 n dimensions when the radius is a function of E naught, divided by delta E naught. Again, ooh, nerd senses are tingling, yes? And so now again, what we're interested, so the way this procedure works is we look at our phase space at a constant energy, we kick the energy up by some small amount delta E and to calculate our volume, and then we let delta E shrink back down to 0. So in other words, what we want to do now is take the limit as delta E goes to 0. What does this look like? It's a derivative, right? That's a derivative. Okay, so in other words, what we want to calculate is the derivative with respect to energy of the volume of a 3D, well, excuse me, a 3n dimensional sphere as a function of energy. And then we evaluate this at E equals E naught. All right. Make sense? Cool. All right, so let's do it. So we want to take the derivative with respect to energy of the volume of a 3n dimensional sphere, which is this thing, pi to the 3n over 2 times r to the 3n divided by 3n over 2 factorial. All right. Now, so you say, well, I'm taking the derivative with respect to energy. Where the heck is the energy? Well, the energy is in the radius, right? So now what we need to do is substitute in our expression for the radius. We're doing on time. All right. So now we just write this as this, 3n over 2 times our radius, you'll recall, is the square root of 2me, right? So it's 2me to the 3n, and then again, you got, remember we got to take the square root, so 3n over 2 over 3n over 2 factorial. So that's what we got to do. Piece of cake, right? Yeah, pi is a constant. No matter how freaky it is, 3n over 2 factorial is also a constant. All we got to do is take the derivative of this silly little thing. And even I, a biological experimentalist, can do that, okay? Okay, so we just do it. So what we get is that this is equal to pi to the 3n over 2, because it's just a constant, divided by 3n over 2 factorial. Okay, so we just pull all my constants through, and then I take the derivative of this silly little thing. And so what I get is I pull down my exponent, 3n over 2. Then I have to take, from the chain rule, I have to take the derivative of the thing inside the exponent. So I get another factor of 2m. Okay. And then times 2me to the 3n over 2 minus 1. Piece of cake, man, right? No problem. That's it. That's our answer. All right, so our density of states. So again, remember, what we're calculating here is the shell volume per delta E. All right, so in other words, what we're calculating is the density of states. So it's the number of states, which is the density of states times delta E divided by delta E. In other words, the thing that we just calculated is just omega. It's the density. So what we just calculated is the density of states. Okay, and so our answer is that our density of states is 3nm times pi to the 3n over 2 times r to the 3n minus 2 over 3n over 2 factorial, where the radius is equal to 2me square root. So that's our answer. Beautiful. Okay, so now now we set out to do what we started. So what we set out to do when we started, if we go back here, is how many states live between E0 and E0 plus delta E? That's the answer. Okay. And so now what we want to do is to show now, okay, that's really interesting. You know, it's not intuitively obvious what this result means, right? It's got factorials. Factorials give me hives, right? What does this thing mean? Okay, so now the next thing we're going to do is to show you how you can take this thing that we just calculated and use it to tell you something interesting about the behavior of the gas. Okay, so now let's apply this thing. So now let's use it. Okay, so now let's answer the following question. Okay, the question is, what is the probability, okay, probability density, okay, and I'm going to call this probability density rho, and I'm going to call it rho of P1 for reasons which will become clear in a second. So what is the probability density, rho of P1, that the X component of the first atom of my gas is equal to some constant value? Guess what I'm going to call that constant value? So in other words, we're looking at the momentum of the first atom, whatever that means. So just we pick one atom out of the box and we look at it. We look at its X component of its momentum, and we want to find the probability that this value of the X component of its momentum is equal to this constant value P1. Okay, make sense? Okay. All right, so what we need to do, so this probability density, rho of P1. So again, remember, we're looking at, it's microcanonical. So in other words, all of the states that we're interested in have the same energy. And that means that they are all equally probable. And so what we want to find is the subset of the phase space that corresponds to the momentum, one of the momentum components having this value, Okay, so in other words, this is going to be equal to the volume of the subset of phase space where P1x is equal to P1. Okay, so that the volume of the subset of phase space where this component is equal to P1, again, because the volume is essentially proportional to the probability, this is proportional to our probability that we're interested in. And then to make this equal to the probability that we're interested in, we have to, again, normalize it. Okay, and so what we do is divide by the total shell volume. And that will give us our probability. Okay, does that make sense? All right, so let's go back to, again, just thinking about one atom. All right, so the one atom that we're going to think about, well, it's this one that we're going to measure the x component of its momentum. How convenient. Okay, so again, if we think about this, the phase space of one atom, it's going to look like we drew previously. So it's in three-dimensional space. And this time I'm going to label my axes this way. So I'm going to call this one now PX. This one is PY. And this one will be PZ. So I just rotated a little bit from what we did previously. But again, the phase space we're interested in is still a circle. Okay, so now I got to think about, so I'm going to, let me try to draw it. So we're interested in, again, this sphere. Okay, so there's our sphere of radius 2m E naught. And again, remember to calculate a volume in this phase space, what we're going to do is to kick the radius of this sphere out by a little bit. Okay, so we're looking at a spherical shell that looks like this. And the volume of this shell the volume of that shell is the total number of states available to our gas. So in other words, this blue quantity here is our total shell volume. Okay, and we've already seen how to calculate this. So now what we need to do is to figure out what this numerator is. We want to find the subset of this phase space where the x component is equal to some constant value. Okay, so in other words, what we're going to do is we're going to start out here at px equals 0, come up by some distance, say here, where px is equal to this constant value p1. Okay, and now I have to try to draw this. Let's see if I can draw this. So let me again go to gray. Let me try to make this thing obviously three-dimensional again. Bet you didn't know when you decided you wanted to be a physicist that you also had to be an artiste, yes? Okay, so now what we're doing with this sphere is on our vertical axis here, we come up by some constant amount and we're interested in all the values of this shell that have that constant value of px. Okay, so in other words, what we're doing is we're looking at a ring hope it's not getting too painfully busy. So we're essentially just taking a section through this sphere. And what we get is a two-dimensional ring. Okay, and that ring are those states that correspond to this x component of our momentum having this value, this constant value P1. Does that make sense? So the volume or the area of this two-dimensional ring, that is our numerator. So our probability density is just the volume of this ring divided by the volume of the shell. Make sense? Okay. Okay, so what we want to calculate, so in other words, if I write this out painfully clearly, our probability density, rho of P1, is equal to the area of this ring divided by the volume of the sphere. Okay, so all we're doing is just finding the fraction of states which have this specific value and dividing it by the total number of states. So it's just fancy counting, right? It's counting for the advanced student. All right, so now we already talked about how to calculate this volume of the sphere. So now let's talk about how to calculate this, the area of the ring. Okay, so again, what we're doing is we have this sphere and we just take a section through it. So in other words, for this drawing, what we did was we went from a 3-dimensional sphere to a 2-dimensional ring by taking a section of it. Okay, and so in the more general problem, what we're going to have is a 3n dimensional sphere, and the section that we're going to take is going to reduce that dimensionality by 1. Right, so just like we went from 3 to 2 dimensions to get that subset, what we're going to be doing for the more general problem is going from a 3n dimensional to a 3n minus 1 dimensional subset. Okay, so this area of our ring, okay, that's going to be equal to the volume. So what did I call this? I called this mu, and our dimensionality is now going to be 3n minus 1 of this ring. So now what we're interested, so to calculate this, we need to know this radius of our ring here. So the radius of my ring, I'm going to call this r prime. So it's a sphere of 3n minus 1 dimensions with radius r prime, whoops, plus, shit. So it's the radius that corresponds to the energy E plus delta E minus the volume of a 3n minus 1 dimensional sphere with radius that corresponds to E naught, right? So in other words, this first quantity here is the radius of this outer purple ring, and this quantity here is the radius of my inner purple ring. Okay, and so now I think we're out of time. And so now what you want to remember for next time is this. And when we come back on Friday, we will explicitly calculate this thing. And what you're going to see fall out of this is the Boltzmann distribution. We're going to get the Boltzmann distribution from this. Okay, so any questions about anything? All right, very good. So then I will remind you that the next time you will be able to talk to me is tomorrow from 9:30 to 1, and possibly outside of those hours too, but that's your safest bet. And then the next time we will formally meet is Friday at noon for our discussion section. Okie dokie. I will see you guys then. Adios.